All right, so now that we're all here, let's see who's virtual this morning. We got, let's see, we got Jack, and that's it, and a bunch of bots. Okay. All right, so my plans for the most amazing lecture ever exploded yesterday. Um, so just I ran into all kinds of problems, and then the PowerPoints that I had made, I had to basically throw them out because everything was wrong or broken, and I had a big case of the dumb. So right, okay, so let's start talking. There's a couple things I want to talk about. One is structs in C, which is uh, like in Java when you define a class and it's got stuff within it. So, you could have, for example, like a book class that has a title and an ISBN number and a whatever, right? Can have all of that kind of compound data objects that mix up a bunch of data types to form something. Okay, so what I thought I'd do is let's just demonstrate one. Made up one in C, and of course I'm going to have my main. Oops. All right, so we'll get to that in a minute. But what I'm going to do is up here above, I'm going to define, and you don't have to define it right here. You can also define these in header files and then include them up at the top, right, for tidiness sake. But for now, it's fine. We can just define it here. Okay, so what I'm going to do is, let's see, look at my notes here. I'm going to make what's called a struct. Okay, and it's going to look like this. Okay, so first off, what I'm doing is using this thing called a type def struct to define a type or a thing. Okay, what goes inside the curly braces is what are the things within that struct. Okay, so we have to decide what kind of structure, what kind of object we're building, and the just for sake of example, let's do something that's got a couple of strings in it and a number. So my thought here was let's do sort of an old school DOS file type, right? So if you go back to like, maybe you guys are a little too young for this, but did you guys ever use DOS? Yeah, like what? That was called civilization. Oh, okay. Oh, you have to run it in DOS box. Yeah, okay. Well, so anyway, in DOS, or MS-DOS, guess, um, which is the operating system that we all ran back in the 80s, okay? And then Windows was actually just a big program that layered on top of it. So you'd boot into DOS and then you'd launch Windows, and then you could quit Windows, whatever. It was really a weird experience. Okay, anyway, in DOS, your file names could only be 8 characters long, and your file extensions could be 3 characters long. Okay, and so you'd have something dot something was all of your file names. Okay, so let's make a struct here that's basically like a DOS file name. Okay, and one could presume, for example, that we could load, if we had a bunch of these things sitting on a hard drive, we could load them into a program and say, sort them or search them or do some, any of the kind of other things that you might want to do with data. Okay, so what needs to go inside this thing? Well, I need a file name. Okay, and how many characters am I going to allocate for my file name? If it's an 8-character file name. Thank you, a null terminator. And this was one example of the dumb that I had yesterday, was I forgot about the null terminator. And so everything was great when I had a 7-character or smaller file name because there was room for the null terminator. But then when I made one to test that was 8 characters, there wasn't a null terminator. And when I tried to print stuff, I got behavior I wasn't expecting. So I had a big case of the dumb. Okay, so file name 9 so that we can include our null terminator. I think in practice, though, what we would have to do is define it as 9 and then like have something that, like when you try to write a file, and if the file name doesn't have the null terminator at the last thing, then it like says no, I'm not doing it, kind of thing. Yeah, so you'd have to have some validity catching. Okay, same thing with the extension. It's 3 characters, but we need room for the null terminator. Okay, and then let me just do also a file ID number. So I don't know, maybe you could like organize your files into different categories this way or something. I'm just making up something. Okay, now that's the structure. What do we call the structure? Well, I'm going to add 2 things here, and annoyingly, they're after the curly brace. And I'm going to call it file and star address. And then I have to put a semicolon. Okay. So what these things are is it defines the name of the object. Now, I've really actually defined 2 names, but one of them's a little special. Okay, so if I want to make a file, I will create one that has, you know, a particular name, a particular extension, a particular file ID, whatever. Okay, what is this address thing? And in particular, what the heck is the star in front of it? It's a pointer, okay? So that's what we want to talk about too, is in addition to structs, we'll also talk about pointers. So what is a pointer? We've used them tons in this class. Huh? It does point to something. Very good. Okay. But in particular, what a pointer is, it's a variable type that's basically a memory address. And it's the memory address of a thing. So it points in memory to that thing. Well, we've used those kinds of things in our assembly code, left, right, and sideways, right? Every time we want to, for example, print something, we have to pass to printf in x0 the address of our format string. Well, that thing is a pointer, right? Because it's the memory location of a thing. Okay. Now, in C, you can use these things. I mean, in some sense, right, they're really just 64-bit integers, right, because they're addresses. But you can use these things, and they're a different kind of data type, even though they're encoded the same as an integer. Well, unsigned integer. But you can use them as variables just like anything else, which means you can also do a bunch of arithmetic with them. Okay. And we'll talk about in maybe a little bit why you might need to do pointer arithmetic in the course of a program. Okay. All right. So what I want to do then to sort of demonstrate this is, so I'm done with that. Let's go into our main routine and let's define a couple of files. Okay. And just make stuff up. So for example, I could have something like this to define it, right? So what is file 1? It is the object that has file name GDB, file extension exe, and file ID I just made up as 1. Okay, whatever. All right, is that good? All right, and then I can make a longer one. So for example, I could do something like this. Example one, that's exactly 8 characters. Okay. I'll just give it the extension ASM for sake of demonstration. And file ID I just made up as 2, right? Nothing special about that. I'm just literally making it up. Okay, good. All right, and then how do we actually access stuff within this? So for example, let's say I wanted to print the file ID of a given thing. Okay, well, I could do something like printf. All right, and so I have to say something like, okay, so if I want to do this, so what's my idea here? I'm going to print the file ID of, say, gdb.exe is number, okay? What things do I need to pass to this? Well, I need to pass something. What's the first string going to be? Okay, well, either example one or GDB, right? Okay, it's a string. But how do I get that out of file one or file two? Huh? Sort of, yes. Okay, how would you do this in Java? File one dot file name. Does that make sense? It's the object file name within the object file one. Okay, and then what's the next one? File one dot extension. And then finally, file one dot file ID, close parentheses, semicolon. Okay, good. And I should tab all this stuff over. Yeah, and of course I've got to return 0. Okay, so let's compile this and look at what's going on. Okay. Oops. Well, I don't really need that for right now. Okay, so there we go. Right, file ID of gdb.exe is 1. Great. Now the dot, by the way, I put that in manually. Right, that's not actually part of the file type or the file object. Um, you know, if you wanted it to be for some reason, you could always do that, but I just did that. Okay, great. So I can access that stuff that way. Okay, now let's go back to here, and I want to print something else for the sake of demonstration. Okay, I want to print where file one is in memory. Okay, which means I want to basically say what is the pointer to it and then print that thing. Okay, does that make sense? Okay, so the way I'm going to do that is, well, first off, let me just do it like I did before. Oops. Oops, file one dot extension, sorry. Okay, now the pointer, Okay, for the printing of this, I typed LLX. Now let's remind ourselves, what is LLX? What data type is that? 64-bit integer displayed in hex rather than decimal. Okay, that's what the X does. Okay, and I know I need to do that because the memory addresses on my gadget are all 64-bit, and so I have to use that kind of data type. Okay, now, how do I get the location of the file in memory? I just do this. Okay, ampersand file 1. So what that gets is it gets the pointer to the object file 1. Okay, and we can see where this thing lives in memory. Okay, good. You know, if you take that thing out, then it doesn't work. Yeah, and I'm like, guys, I have to admit, it's been a while since I've done C, like this kind of level of C. And in fact, I never actually did true C. I did C++, although at the beginning of a C++ class, you're really not doing a whole lot that's different than C. I think it's later. Plus, where I went to school, I want to say that, right, so how do we lay out the programming curriculum, right? We got CS111 and then CS211. Well, a lot of schools, and the one I went to, it had like a CS111 and then a CS112, and then you would get into things like data structures and whatnot. So your second semester programming class, you would be going into a lot more detail about some of this stuff. But okay, whatever. So let's just run this, okay, and there we go. Okay, so the file ID of gdb.exe is 1, great. The memory location of gdb.exe is 7f, blah, 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 blah. Okay, all right, good. So what I want to do a little bit is look at how this is going to translate into assembly to some extent, but then also pipe this thing through GDB so we can actually look at the memory. Now, this memory address 7F, blah, 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 it will actually look a little different when we do it in GDB. I mean, it won't be that exact same memory address, okay, because GDB. Okay, so so the first thing I'm going to do is I'm going to compile to assembly. And remember, I can do that with the gcc-S command. But I'm going to name my file type .s, not .asm, because this is machine-produced assembly, not hand-produced assembly. Okay, now let's look at what we got. Okay, so this is the assembly that was produced by GCC for our program. Okay, now a lot of this, right, is usual stuff. We've got some strings up here, right, our format strings. We've got our main function. Okay, it's going to do a bunch of stuff. There's a bunch of stuff down here at the bottom, right, which has, our file names, our file extensions, etc., right, as strings that can be loaded in. And then if we go back into the code, right, okay, it's going to be storing a bunch of crap to the stack, basically, storing all the data, and then we're going to have some printf stuff, right? Okay, so what is it going to do though for printing printf, right? So it's loading, for example, well, let's see, load W2. Okay, so like for example, W2, right? What's it doing? It's loading it from the stack pointer offset by 56 bytes. Okay, and then 4 lines down, it copies that into W3. And then eventually it's going to branch to printf, right? Well, let's think about what we were printing. We were printing string, comma, integer in the very first printf, right? We only did 2 of them, okay? So if we want to print string, comma, integer, then what information do we have to pass to printf to do it? What's got to go in x0? Address of the format string. What's got to go in x1? Address of the first string, which is in this case the file name. x2, address of the extension string. And then W3 is going to be what? The file ID number. Now, why is that in a W and not an X? Because I defined it as an int, not a long int, right? So it's a 32-bit object, not a 64-bit object, hence why it's in a W and not an X, okay? And that's only because I just chose regular int rather than double. And then we can branch to printf and everything gets printed and yay, okay. So, then, right, so if I'm printing this object, right, all of this data is sitting on the stack. And if I want to load that data, I'm loading it basically from memory addresses that are relative to the stack pointer. Okay, or I could just load in the actual memory address if I knew that number in advance. Okay, so what I want to do is I want to go back and I'm going to add one, I'm going to add basically one line to my C program so that I can go all the way to a certain point in the program without it terminating, okay? And, well, actually, you know what? No, I don't need to do that because I've got the return. I can just do it, wait and do it there. Okay, so what I'm going to do is I'm going to assemble this assembly and then link it as if we wrote this stuff from scratch. Okay, now we didn't really, but let's just pretend we did, okay? Okay, the other thing I'm going to do is, where is the return command? It is at line 64. Okay, so my load pair and stuff like that. So 59 is where I basically start getting ready to terminate the program. Okay, so keep in mind line 59 for in a moment. Okay, so next what I'm going to do is I'm going to rename it for reasons that'll become clear in a moment. Okay, the reason I named it something different is I didn't want to overwrite the executable I currently had, and also GDB gets a little ornery if you're running something and it finds both an assembly and a C file to refer back to. So, okay, whatever. Okay, so now let's do GDB, and we're going to do the Structs test program. Okay, so I'm going to put in 2 breakpoints, one at main, basically right when the program starts, and the other in let me blow this up, the other one at line 59, which is right when we start to get ready to terminate the program. Okay, so then I need to run it. Okay, and at this point, my stack starts to get expanded, and so I'm going to basically skip ahead to line 59. Okay, and I can just do that by doing continue, and that will do all of the stepping until I hit line 59. Okay, so what have we gotten from our output? We see that, okay, great, the file ID of blah is blah, but the memory address is blah, blah, blah 068. Okay, great, whatever. Let's go dig into memory and see what's sitting there at 068. Okay? All right, so also while we're at it, what is our stack pointer? It's 040 currently. All right, so let's do X. Let's do 32, well, let's do 64XW stack pointer. All right, so I probably did way too much here, but that's okay. Great. You know what, for right this instant, let me switch. Let me put the same thing on both screens. Okay, so let's dig into the memory. All right, what did we say it was? 048 or 068, excuse me. 040 is the stack pointer, but the memory location, the pointer to my object was 068. All right, so let's go to 068, which starts here. It's the second half. Okay, now we do have to worry a little bit about the Indianness. So what should we expect to see in our thing here, right? What was our file name? GDB, right?
Okay, and then of course right after that we have
Right after that, what do we have? The obligatory null terminator. Excellent. Okay, then we've got right after that a bunch of zeros. Okay, and it's not until here, oh, and there's some zeros right there too, right? Then what do we have? 657865. That's EXE. Where's its zero? Yeah. Okay. And then a bunch of padding zeros, and then where's our number? Right there. Okay, so this stuff it's wasted a little bit of space. Now, what I did when I was working on this yesterday, and I had a big case of the dumb, I defined my file name as an 8-character string. And then I made an example 1, that had 8 characters. So what happened when I wanted to print that file name is that it printed the file name and the extension. Okay, and the reason was because the extension started in memory, that string, right after the file name string ended. But there wasn't room for the null terminator. I didn't leave room. Okay, so I got a big, hot piece of garbage, which is not what I wanted. And then I was like, oh, right, null terminators. I'm a bonehead. Okay. So I went back and, fixed it. And of course, that meant that I had to throw away about an hour worth of PowerPoint slides. Okay. So it happens, guys, right? So, okay. All right. So this is how this stuff looks into memory. Now, if you are, for example, what's pointer arithmetic going to mean? Well, let's say that you want to access the file extension out of this. If you know the pointer to the start of the object, how many bytes past that would you find the extension? Okay, in this case, how many bytes past? Well, let's look at our example, right? So where are we? We're here, GDB, null terminator, bunch of zeros, null terminator, okay? And let's think about why that zero is all the way down there. Well, what's the maximum length in terms of the number of characters without the null terminator that I can have? 8, right? And then the 9th one is the null terminator. So here's 4 bytes. Here's 4 bytes. 9th byte null terminator has to go there. Okay? So, how many bytes past so if my pointer is 068, blah, 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 068, that's where the structure starts. How far past that is the file extension? How many bytes off? 9. Okay, why 9? That's correct, but why? Right, and each character takes a byte, right? So I know that this thing is going to store it in memory basically right after the file extension, okay? And then, or sorry, the thing, right? So this 00 is my null terminator from like the maximum length string I could put in. Then I've got my file extension. There's its null terminator. Okay, and then why do we have all these extra zeros there? So why is it that the file number doesn't come until later? Well, what kind of data is the file number? It's an integer, okay? And for whatever reason, the compiler has decided to align that onto an 8-byte boundary, okay? I think that's probably because the LDR instruction is capable of loading in 64 bits at a time, right? And so, but what it's not doing is loading a byte, loading a byte, loading a byte, loading a byte, loading a byte. Like it's literally loading all the shit in at once. Um, and so it probably has to be 8-byte aligned for that to be Gucci. Whereas strings, how do you load strings? 1 byte at a time. Okay, you don't really have much choice. Okay, so does that kind of make sense? All right, so there's sort of a quick demo on structs and why you would therefore need to do pointer arithmetic. You would have to do pointer arithmetic, you would have to know the size of the objects, like in terms of how much memory was allocated for them. 9 bytes for the the file name, 4 bytes for the extension, and then the integers in this case are 32-bit, right? So we know that that's 4 bytes for the file for the file ID, and right. So if I defined a file, like let's say that I had 6 different integers in here, they would all be offset by exactly the length of an integer in bytes. Okay, 4 bytes in this case for 32-bit precision. So, okay, great. All right, so next, let me actually switch the screen. Okay, and let me load preview. And of course, it's not going to load the correct window. Okay, now let me switch to preview because it's all janky. I think I need to do transform, fit to screen. There we go. Okay, so let me blow this up a little bit more. And let me switch the input here so that you guys can see it. Okay, so we're now on my computer and I'm actually going to put, oops, let me switch them this way. Because I don't want the Pi to fall asleep on me. Okay, so the next thing we're going to talk about is what are called atomic instructions. Okay, so first off, forget any of this business. Forget what I've got on the screen. What does the word atomic mean? Huh? Right. What is atom? What is an atom? Huh? It's undividable, literally, is what the word means. Okay, now there's this one minor problem with it. They actually are dividable. But we didn't know that for a while. Well, there a little some energy gets released. Yeah, if you do lots of it at the same time, then lots of energy gets released, and that's called a nuclear weapon. Okay. Well, if you just split one atom, that's not a big deal. And there's atoms in this room splitting right now. There's atoms in your body that are splitting right now. It decays. There's usually two different elements that it decays into.
So decays into different elements.
Right.
So half-life kind of.
Well, half-life is how long it takes for that to do it, but on average, right? So yeah, so there's probably a molecule of uranium somewhere in your body, or I mean, atom, right? And yeah, it might have just decayed. I don't know because there's only one of them. Yeah, it's called yeah. There's not enough of it, and the energy that's released from one single atom compared to the energy released from um, your cells breaking breaking bonds on ATP, right? Breaking that phosphate bond, or yeah, is that right? Yeah, the chemical energy is a lot bigger. Okay. All right. Anyway, you want to harness it, that's called a nuclear reactor. You want to really harness it, that's called a nuclear weapon. Okay. Fine. So atom means unsplittable. Okay, or undividable. Now, there are two senses of the word in uh, the architecture, like architectural stuff. Okay. One of them, all right, and would somebody please note that we are on page 1319 of 8248? Okay, so this is the architecture reference manual from ARM, right? All 8,248 pages.
It's a fun PDF.
It is a fun PDF. I should print this. Can you imagine the look on Westfall's face when he got the printing budget? Like, you spend how much? Yeah. Okay. So there are two senses that atomicity gets used in programming. Okay. And so what I want to do is I want to show you one of those things. Okay. And so could somebody write down page 1319 for me so we can come back to it later? Okay. The first one is there are a bunch of instructions that are called atomic. Okay. And what these things do, let's say that I wanted to load something from memory, add it to a register, and store it back to memory. Up until now, how many instructions would that take? Take 3. Load it from memory into a register, add 2 registers, output back to whatever address in memory. Okay. ARM defines a single instruction that can do that. Loads, adds, writes, all in one instruction. Okay. And that operation is what we call atomic in the sense that you can't split it halfway, right? Once that thing runs, the whole thing runs. All right, so let's actually go back into on the Pi and program one of these things. All right, so let me make a new project, and I'll call this atomic, and then I'm going to make a new file. Which I'll call atomic. So I need some data, I need some text, I need a global main, I need to do my usual my store pair load pair business. And then I need to move W0 to have 0 in it and return. Okay, great. All right, so let me save this as atomic.asm. Excellent. Okay, so let's use this load add instruction. Okay, first off, how would I do it without the load add instruction? Well, first off, let me actually just make some extra room on the stack here, so I only have to expand it once. Okay, so let me just move, and I'm just going to make up some numbers here. Okay, I'll put x0 on the stack. Okay, and so let's pretend that x0 that I don't have 05 in x0 anymore. Okay, so to do that, to sort of force it, I'm going to clear it by moving the XCR. Okay, so if I wanted to add whatever's in memory at the stack pointer, I would need to load X0 with the thing at the stack pointer. I could say add it together with X1, and then I could store it back to the stack pointer. Okay, so if I were to execute this, what would end up at the stack pointer when all is said and done? The number 8, right? So I loaded in 5. I happen to have 3 already in a register. I added the two things together, and I dumped it out to memory. Okay, so that would do exactly the same thing. All right, now, let's suppose that instead I did this. Well, okay, so let's in fact, well, we don't need to run it. We know what's going to happen, okay? All right, so let's instead say that I did a load add, LD add, right? And the syntax for this is on the other screen, right? If the, and what's on the L, what's on the, what am I streaming currently? Okay, I'm loading the, streaming this. Okay, so what's the syntax for this? I need to pass LD add 3 things. Okay, so there's 32-bit variations and 64-bit variations. They're basically the same thing, right? But I have to pass it 3 pieces of information, 2 registers, and the location in memory that I'm going to pull something from. Okay, all right. So what is this going to do? Is it's going to load whatever's in memory into register X sub S. It's going to add that to whatever's in X sub T and store that in X sub T, but then dump that immediately out into memory. Okay? All right, so in this case, we need to, where is the number 3 in our register? And let me switch the Elgato, switch back to the Elgato. Okay, where is the number 3 is in memory at X1, okay? And so if I'm going to load in someplace, I need to load into X0. X1 is where I'll have the thing I want to add to, okay? So what's going to be in X, or actually it should be plus 16. No, 8, because I'm a big dummy. Okay, so what is in X1? 3, okay? If I load what's at the stack pointer, oh, I'm sorry, I wanted this, not plus 8. If I wanted to store, I'd put it at plus 8, so I don't overwrite what I've got. Okay, so what is this going to do? It's going to pull out of memory whatever's on at the stack pointer. What is at the stack pointer when I get to line 19? 8, because it's after I did that addition and then store, okay? All right, so 8 is sitting at the stack pointer, great. I'm going to load that thing into X0, I'm going to add it to x1. Okay, so what do we now have? 11, and then I'm going to dump that back out to memory. Okay, so let's demonstrate this. Huh? Uh, yes, I think so. Okay. Well, let's find out, right? What did I call this? Atomic. All right, so as-g atomic.asm. Womp womp. What's the error we got? Selected processor does not support the instruction LD add. Okay, so that was womp womp number 2 of yesterday. No, it's not a virtual machine. I am running this natively, right? I'm on a Pi here. I'm not emulating anything. Although actually I do wonder if I did emulate this, whether it would work, right? Uh, okay. Why doesn't it work? Well, let's take a trip to Wikipedia, shall we? What is the processor that's inside the Raspberry Pi 4? It's an ARM architecture, yes, but what is in there? Do you guys happen to know? No? It's a Cortex A72. Great. Okay, manufactured by Broadcom under license. But, okay, so you can read all about the history of these lovely little machines. All right. And let's go to processor. All right. Developed by Broadcom in cooperation, right? Blah, blah, blah. All right, so here we go. Raspberry Pi 4 uses a Broadcom BCM 2711 system on chip, 1.5 gigahertz, 64-bit quad core Cortex A72 processor. Great. Let's click on this guy. And wait for this. It's funny because I think it was Dr. McCartan Lim and I were talking last night when I came back into work, and that like supposedly Eduroam is getting DDoSed, right? Which like I don't think would affect our network traffic, but it would affect your ability to like authenticate with the network. But yeah, so right. Okay, so great. The ARM Cortex A72 microarchitecture implementing ARM v8A of the instruction set. All right. Well, and then blah, 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 blah. It was announced in 2015. Okay, let's see what it's got. Pipeline processor, DSP, digital signal processing, and the Neon SIMD units are mandatory per core, meaning that if you license the model from ARM and you build a processor, you're not allowed to build it without the Neon units, right? You have to do it with the Neon units if you license this particular model. Okay, bunch of other stuff, right? Super boring. But what I want to look at is ARM v8A. Okay, so ARM v8A, announced in October 11, represents the fundamental change to the ARM architecture. It adds the optional 64-bit architecture and named AArch64 with this new instruction set. Okay, blah, 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 blah. Apple was the first to release an ARM v8 core with the iPhone 5S. Did anybody have one of those? Yeah. Okay. Uh, I didn't. Let's see. I had my iPhones were iPhone, the first one. Okay, and then a 4S, and then a 6S, and then my current 10R. Huh? Yeah, 4 years or three. Yeah, 3 years. Yeah, it was solid, but I finally pulled the trigger on the 10R because I was getting ready to go to France with Dr. Rhodes, and I'm like, this battery doesn't last very long anymore, and I'm going to be guiding students around Paris, so I kind of need a phone. Um, yeah. So anyway, and I've loved it. I've actually my 10R is fantastic. Um, okay, so here's the problem. The Cortex A72 is an ARM v8 architecture, but not to be outdone, in December 14, what did they announce? 8.1. And guess what is included in that? A set of AR64 atomic read-write instructions. Which LDAD is one of those? Okay, so the ARM architecture, you have to have hardware that actually is 8.1 or higher compatible for this to work. Now, this is one reason. So I would fully imagine that whenever the Raspberry Pi Foundation releases the Raspberry Pi 5, whatever that's going to look like, okay, that it will be at least 0.1 compatible and probably more like 0.4 or something. Okay. So, whenever that comes around. Now, I don't think they're really going to be in much of a hurry because what's the purpose of the Raspberry Pi? It's cheap, it's very power efficient, and it's perfect for like students basically, right? It was designed to be a very inexpensive single board computer that without a whole lot of fluff you could give to millions of students and they could start doing cool stuff, right? It is not your latest iPhone. Okay, latest iPhones are running the latest version of ARM, right? Apple has a license to the instruction set. Now they designed their own silicon that implements that instruction set, but they license the instruction set from it. So if I were to Friday or whenever go to the Apple store and pick up one of the um, new M1 powered Macs, okay, right? Because I think we talked about how they're switching their processor line over to ARM to match what's in all of their mobile hardware. Okay, so they're custom designing, desktop class chips basically that are ARM architecture. And here's what's freaky. Um, so somebody ran, and then they have software emulation for x86, which is what the current Macs use. Somebody ran a benchmark, and for single core performance, the M1 emulates x86 faster than an x86 processor executes it natively, which is just like bonkers, right? Yeah, so Intel is going to have a bit of a run for their money here. Huh? Well, I don't think the memory is actually on the chip itself. I think they are still separate dies, but I think it's all in one package, right? So there's a difference between the you do it because it's faster and it's more power efficient, right? Um, Theoretically, yes, but I mean, RAM doesn't generate that much heat. It would, but we've been using integrated graphics for years, right? And if it's designed, I mean, right, think about it this way. Apple has had basically more than 10 years of experience designing things for low power mobile applications, right? And so it shouldn't come as a shock. Which three machines did they first release this thing for? Two laptops and the Mac Mini. Okay, so anyway, so that instruction is not available on the Raspberry Pi chip. Okay, womp womp. Um, Now, there's another sense in which we can use the word atomic, and for that I want to go back to page 1319 of my manual. All right, so go to page, what was it, 1319? Okay, so there are a bunch of instructions that are of the form, well, let me just find it this way. Okay, so let me start with this one here, okay? There is a different set of instructions that to some extent we can call atomic, okay? And they're not atomic in the sense that the instruction, I mean, it's a single instruction, so sort of by definition, it's unsplittable. But what you would use this for is to make larger units of several instructions that were atomic as a unit, okay? And what we mean by that is either the entire unit of instructions runs or none of it does. Okay, so it's you either get all of it or none of it kind of situation. Okay, so it's a slightly, I mean, maybe we should call these molecular instructions. I don't know, but whatever. Okay. Um, okay, and the these in the manuals are usually called exclusive instructions, okay? And you've got, well, we had LDR. What did LDR do? Loaded a register with something out of memory, okay? Well, there's also LDXR, okay, which does the same thing. It loads a register from an address in memory, okay? But this thing called the PE, and I forget what that stands for, marks the physical address being accessed as an exclusive access. This is exclusive access mark is checked by the store exclusive instructions. Okay, so if we have LDXR, we also have STXR for store exclusive. Okay, and that's the one that was on page 1319 that I want to talk a little bit more about. Okay, so if I load something from memory, that memory address is marked by this thing called the PE as basically being special. Okay, and the specialness is that other threads, okay, so we're running on a quad core processor, right? But there's only one big pile of memory, right? So other programs could be trying to use memory in that same segment, or maybe different threads within a program. That's actually more likely what would happen, right? So for example, let's say that you're a programmer for Adobe, right? And you want to do in Photoshop, you've got like all the different image filters to do like make it look black and white or sepia or whatever, right? Well, all of those things under the hood, what would be really smart uh, for Adobe to do in terms of programming? If you've got a big old image and you want to make it black and white, and you've got a 4-core processor, then why not divide the image into four quadrants and have each core do it to one of the pieces and then sort of assemble all the stuff at the end, right? That's a very parallelizable process. Same thing with video encoding, right? Okay, and then by doing so, what's the benefit to the user? It runs faster, right? Because you're using all of your hardware to do it quickly. Okay, now, I mean, realistically, right? How long is it going to take to do sepia tone in Photoshop? Probably pretty instantaneous anyway. But what about if you're doing something on like a gigantic 100 megabyte TIFF file or 200 megabyte TIFF file? Now you might ask, why would you ever work with a 200 megabyte image file? I have manuscript images, high quality manuscript images. So yeah. Okay. So right. So you might be in a situation where certain pieces of data need to be accessed by more than one um, thread. Another good example of this would be, we never got it fully working, but let's take, for example, the GPIO stuff. Okay. The GPIO, um, and I wonder if actually this is the reason it wasn't working. I wonder if I needed to store exclusive rather than just store when I wrote to the, huh. Okay, I'll have to think about that. So anyway, how did the GPIO work in theory? Okay, there are on the Pi, right? There's the chip, and the different pins and the chip that controls all of that is memory mapped. Okay, so what does memory mapped mean? It's here, but the operating system is going to say, all right, I'm going to let this part of that chip be at memory address blah, and if anybody wants to access the input output, they're really just accessing a little segment of memory. And the fact that it's a separate chip is sort of invisible to them as a programmer. Okay. Well, there's only one GPIO chip, right? And so there's only one segment of memory that the operating system is going to allocate for those things. And hence, um, if I want to be using the GPIO, I might need to do a store or load exclusive to say, hey, other programs, hands off my GPIO. Okay, so with the GPIO, reading from it's no big deal. Okay, you can read whatever you want. It's writing where you have issues. Okay, because with the GPIO, how did I turn pins on or off or configure them for different purposes? I wrote bytes to an appropriate spot in the appropriate memory address. Okay, so that was the whole point of the memory mapping. So I had to write something to memory in order to do something with the GPIO. Okay, well, so let's go to page 1319. This is where it gets dicey, right? Because let's say that the I have loaded from an address, and now this address is being marked as exclusive. Okay, and the PE is either going to grant me permission to do a write or not. Well, my program needs to know whether or not that happened. Okay, so if I wanted to write to that address, I would like to know, was that successful, that write, or was it unsuccessful? And the STXR gives me the ability to do that. Okay, so STXR, I specify not two things, but three: what I want to store, where I want to store it, and a register to get updated with whether or not the store was successful. Okay, does that make sense? Okay, if the store is successful, that register gets overwritten with a 0. If that store is unsuccessful, it gets written to a 1, or written with a 1. Okay, which means that if I did an STXR, what's the thing I'm going to do immediately after that to check, hey, did the write happen or not? I'm probably going to do a CBZ or CBNZ, right? Did the write happen or didn't it? Okay, so remember, 1 is the write did not happen. which does require a little bit of mental gymnastics, but that's okay. Okay, and so what I could do then is, so let's say I was writing a program and I was trying to write to my GPIO stuff, but another program was running that was currently using the GPIO stuff. I could say, oh, my write was unsuccessful, try it again, try it again, try it again until it works. Maybe I put like in a 10-second pause or something, I don't know, right? And then um, if so I've got these instructions that allow me to mark an address as being exclusive. So what do you think I should also need there for? Like to unmark it, to release it. Okay, and there are release instructions also. Okay. So there are instructions for releasing control over a memory address when you're finished with it. Okay, does that um, let me get the so last thing, right? We're done for the semester. Um, some of you guys owe me still a lot of stuff. Well, I mean, a lot of you owe me Logisim 3. Everybody still owes me Logisim 3. Some people don't owe me anything but Logisim 3. Um, some of you owe me a lot more than that. So, when is the drop dead absolute latest time that you can give me anything? The 24th at noon, so a week from today. Okay, 12:01. I've even configured Canvas to lock everything at 12 Tuesday next week. No, you can still get to the Canvas page, but none of the submissions, you can't. Yeah, you can view everything, but you can't submit anything at noon. Yes, no, I wouldn't do that. I do not know. Yeah. So you guys do need to be archiving your own stuff, right? Let's not be stupid here. Okay. Okay. So that said, um, if you submit something sooner, then I'm going to look at it the first chance that I get, no matter how many emails you send nagging me about it, Walter. Um, okay. Not to name any names or anything. So, right. If you submit something earlier, I'll look at it. And if there's a problem, which, you guys sometimes don't think of test cases that I do, and I find something that breaks your code, and guess what that means? You get to fix your code, okay? Kick it back to you. Okay, but if you submit something at 11:15 on Tuesday next week, what's probably not going to happen before noon? I'm not going to be able to check it, and even if I am and I find a problem, are you going to be able to fix it in 10 minutes? Probably not. If it's that small of an error, I probably won't even kick it back to you. Okay, because that's like typo level. Okay. All right. So let's not be idiots. And yeah. All right. I think that's it, Jack. Hope you had fun online, bro. The other thing would be turning in your Raspberry Pis. Um, basically, just come by whenever you're ready to turn them in. Which, if that's Tuesday at noon, that's fine too. You do not need to worry about nuking the SD card or anything. I will re-image them before the next time I use these, because by next fall, I'm sure there will be a newer version of the operating system, right? Because right now we're using a beta, and I'm sure there'll either a more bug fixed beta or the real deal, the full release. So you don't have to worry about that. But that said, USB thumb drive, back up all your crap on it because when I nuke these things, everything on them's gone. So if you want to save all your programs and all your stuff, I would. Um, if you want to buy the Raspberry Pi and keep it, for those of you who are currently borrowing one, I'm going to look into how to actually do that with the business office. I'm sure there's a way we can do it, but basically you just pay the college for the cost of the thing, and that's that. Um, I'm hoping it's that simple, because if not, I'm going to be pissed.
You're not surcharging us for the work you did on the operating system.
That sounds like a really great idea. I also think that people whose name is Evan should have to pay a PITA surcharge. Yeah, okay. And yeah, so, okay. Yeah, when I went over there last week, the person I needed to talk to was out for the day, and so anyway. All right. We'll get you a receipt, don't worry. Okay. All right. Have a good rest of the year, gentlemen. What's left of it.